Hello, so very welcome to my talk. I'm Trung. We also have 3 team members who will not be presenting here, who is Antonio, Kim, and Dave. So a little bit about myself. My Twitter handle is on the screen. I'm currently an undergraduate computer science student at Purdue University in the US. I'm from Vietnam. Currently, I'm focusing on macOS and iOS research. I used to blog about CTF write-ups or challenge, but I have ceased from doing so since quite a long. So today's agenda, first we'll discuss the current state of iOS research. Then we can look at our desired goal in building an emulator. Then we'll talk about how we implemented it, and also the ways that we can use TruEMU for research. Then we'll talk about its future and roadmaps. So let's dive right in. So we need to talk about the current way we are doing iOS research. The most common way is to use real device. And you also have a few options for that. First, you can use something called security research device by Apple. This is a real device. However, the main problem with this is that you have to sign NDAs, and you're obligated to report all of your findings to Apple. Other options is to use internal device. So these devices are mostly stolen, and because it's only limited to internal use only, so you have some legal issues there. So it might not be preferable for most of researchers. And also, these devices are really rare because they have to be leaked. On the left is some of these devices, and on the right is the cables that you'll be using to debug this device. Next, you can use off-the-shelf jailbroken device. So these are devices you can get from the store, but you have to hack it first in order to do research it. So it's already a high barrier to deal with. However, there are some recent research with the checkmate exploit, which allows you to do debugging, provided that you can build yourself cables on the right, the pictures on the right. This is set up by another researcher. Another option is for non-jailbroken device. These devices are highly sandboxed and pretty secure, so it's really hard to do work with it because you're only limited to the panic log, which is not interactive at all if you want to do kernel debugging and hacking or something like that. You can also use ARM marks. And with all of these problems posed by real device, we try to solve some of them using emulation. So some options for emulations, well, you have a third-party commercial iOS emulator. These are pretty popular, pretty state-of-the-art, really cool, but however, they are pretty expensive, so I never try it personally. And if you want to dive into more low-level stuff, such as iBoot or SEP, it is also limited to on-premises only. So unless you are a big company or a government agency, you probably cannot get access to it. You can also use VM Apple, which is a Mac VM provided by Apple. These are also limited in customization, but some people have managed to do some really cool work with it. And you can also use RLAB security or QEMU port. So these are presented at Black Hat Europe in 2019. But however, the problem is that they only support 2 iOS versions only. So that's pretty limited. They also have very limited hardware support, and it also has it's also really hard to maintain because of the code quality, and it's also abandoned by now. So we try to build an emulator that can solve as much of the problems that posed by these methods as possible. So now let's talk about its design goal. So we want a free-to-use iOS research emulator, so it's as research-friendly as possible. And by that we mean we want to have a wide range of iOS version support. We also want to debug the kernel easily, and we also want to use it for fuzzing. So with these design goals, we have come up with some very notable features. First, the emulator model actual hardware. So it tries to behave as close to the real hardware as possible. It supports a wide range of iOS versions, ranging from iOS 14 to iOS 16, which is currently still in beta. We also support SecureROM and iBoot stuff, but that is very experimental, very new. You can also debug the kernel with it very easily. It also has USB support, so you can install real iOS. It also supports some custom CPU features by Apple, and the best part is that we are open source, so you can check out our repo, which is in the QR on the slide. So how did we do that? Well, there are a lot of challenges, and we will walk you through the general ideas. So how does the new device get modeled? Well, first we will look for the information in the device tree. Then we'll build a stub model, so a model that does nothing, but basically logs every access by every instruction from the CPU. And with these tools, we can do dynamic and static reverse engineering to see how does the hardware behave, how does it work. And then once we know the protocol, we can write emulation code to emulate the needed response, and then we will have a device that is emulated. So let's walk through some steps. First, the device tree. The device tree can be found in iOS firmware, which you can download from Apple. The best thing about it is that it contains a rich amount of peripherals information, and is used heavily by the iOS kernel to match drivers. So let's have a look at an example entry. So on the screen is the device tree entry of the GPIO controller. So on the left is the property name, and on the right is values. Let's have a look at some interesting ones. So the arrows is currently pointing to the comparable property. So the comparable property is used to match drivers. So it will look at the strings in the comparable property and then find the appropriate drivers for the correct device. And it will, another interesting one is interrupts. So this is basically a list of interrupts that the device will use. So in this case, the GPIO will use hex 83 to hex 89 interrupts. You also have the rec entry, which is basically where the device is in the memory. So basically it's MMIO address. And you also have the hash GPIO pins, which is shorted for number of GPIO pins this device has. So with this information, we can build a submodel. So we map a dummy memory region into the MMO address in the device tree. Then on each write or each access by the CPU, will log them and then print a backtrace. And with the backtrace, we can travel through related code to see what is the logic of the software, what it's trying to do, something like that. And we can also even try to drive the interrupt lines to see how those interrupts are processed. So here is an example log from for the display controller. So I don't know if you can see it, but we have the offset the CPU is writing to, the value, and also the backtrace PC, so we can easily navigate to the iOS kernel code. Next is a really interesting CPU features, a very custom one by Apple. So it's called SPR-GXF. This is used in both iOS kernel and also in userland browser. It's basically a custom privilege level created by Apple. So how does this privilege level fits into the normal one, you may ask? Well, let's have a look at the normal privilege level model. So we have EL3 to EL0. The higher number, the more privileged it is. So EL0 is the user space, and EL3 is the supervisor. So for GXF, it basically creates GL2 and GL3 is laterally from the normal one. So GL2 is guarded mode for EL2, so it is more privileged compared to normal EL2. So GXF is shorted for guarded execution feature. So you have a guarded execution level. To enter it, you use the genter instruction, which is a non-standard one. And you can use gexit to exit from the guard mode to normal mode. So the difference between guarded and normal mode is that guarded mode can have different permission. So you can create pages that can only be written by guarded mode but cannot be modified by normal mode. So here how it works. So on the screen is the normal page descriptor. So this describes how a page. This describes the permission of the page. So if it's readable, writable, or executable. So you have so the colored bits are the ones that used to determine the permission. However, Apple changed the definition of this bit, and they convert into index. So they match it into an index instead of passing it a permission itself. And the index is used to look up on a permission register, which is 64-bit. And you can have 16 permission index. And each permission will have 4 bits, which will describe the permission each page have. So 2 bits for guarded mode and 2 bits for normal mode. So permission bits on page level now becomes indexed for a system register. So how it is used in iOS kernel? Well, Apple has a thing called page protection layer, which is normally shorted for PPL. This contains security sensitive code. So you can have, when you compare the size of guarded code and normal code, you can see a large difference. So for my comparisons show that they are more than 300 times smaller for guarded code. So which means that security sensitive code has less attack surface. When you hack it the normal mode, you also need to hack PPL in order to do more fancy exploitation primitives. So you can jump from guarded mode to normal mode, but not the other way around. The other way is being used is for JIT. So browsers tend to use JIT to speed up the execution process of JavaScript. So what it does is compile JavaScript to native code. So to do that, it creates pages that are both writable and executable. However, these are some problems. For JIT page, you constantly need to switch between these modes. For when you're compiling, you need to switch to write mode, and when you're executing, you need to have it in execute mode. So changing the permission generally takes a lot of, it's pretty slow, or it takes a lot of work from the CPU, so performance is degraded. So Apple designed SPR to fix this problem to improve the speed of the JIT compiler. So let's have a look at the process of changing. So this is an excerpt from the method that change the write protection mode. So this is a method that change between read execute to write or read write and vice versa. So on the left is the path for execute mode, and on the right is for the write mode. So the difference between two paths is shown by the top arrows, which the values are read from the different location. So the first location will contain the values that will configure the page to execute mode and or write mode. So the MSR here is the trick. When the CPU finds the MSR instruction, it will change the permission of the page that is SPR configured. So you can see there is no syscall involved, no trapping involved, so it runs really fast. So with this completed logic, we have to implement it in QEMU in order to add support for it. So how do we do that? So first thing first, you need to decode more instructions, which is the genter and gexit. These are custom instructions. You also have to rework the page table logic because the CPU no longer understands the page permission the same way. However, we still haven't figured everything out yet. So, and the QEMU TLB still have some limitations. So we still require a TLB flushes, which may slow down the performance when the permissions are being changed. Next, let's talk about USB. So why do we want USB emulation, you might ask? Well, we can use it for restoring. So restoring is a fancy way of installing an operating system for iOS device. So when we restore an iOS device, it's basically installing an iOS on the device. USB is also really useful. You can use it for networking, for example, like SSH. And you can also connect the device to Xcode using USB. However, to implement USB, there are some challenges we face. The first problem is that iOS already has USB drivers for Synopsys controllers. If you never heard of them, they build hardware IP, basically the controller. However, the datasheets tends to be paywall, so you need to have a deal with Synopsys in order to get a documentation on how the device works. However, there is another way around that. Here on the screen is an excerpt from a QEMU code. So in the comments, there are really interesting lines. So they link a documentation for the device, which, interestingly enough, is freely available to the public. So when Synopsys doesn't give it to you, let the other hardware manufacturer give it to you. Because hardware, for example, or even Intel, when they make some boards which use hardware IP, they release documentation for it, which the USB section for it is basically a copy from the Synopsys one. Okay, so the second problem is that actual iPhone use newer Synopsys controller. So documentation for the newer controller tend to be sparser, so you have less of them, or fewer of them, so it's not as much as available compared to the old controller. We used to work around this by forcing iOS to load drivers for the old controller. However, luckily, we are able to implement the new controller by now. So that's for the controller. The USB also have the USB bus that we need to implement it. So if you don't know, USB has two sides. One is the host side, which is generally your PC. And the other side is the thing you connect to your PC, which can be your flash drive or your iPhone. QEMU does not support device mode because it's built to emulate a PC, so we have to implement the support for that. So how do we do that? Well, we connect the iOS VM to a USB host to Unix pipes. On the screen is a simple diagram of how it works. So on the top level, you have the software running. The software will talk to the controller, which can be the Synosys USB or the ESCI, which is the USB 2.0 controller. And this controller can talk. These controllers are emulated in QEMU. So, and this controller will talk to a physical layer, which we implemented it through some proxy device, and this device will talk to each other through sockets, Unix sockets. So how can we use it for research? So, well, let me show you. So, okay. So in the first demo, we will try to restore iOS. So here we are starting on iOS VM. On the left is the iOS, and on the right is the Linux VM, which acts as a host. We run iDevice restore on there, and the restore has started. You can see the process bar is creeping up. We're speeding up the process here because restore tends to take a few more minutes. There we go. The restore complete successfully. You can see it says restore finish, and the device will restart. We override the restart behavior to make it stop, so it makes it easier for recording. So the process took 11 minutes. Okay. Next, I will run it. I will do a live demo. So here we will start an iOS VM. I am running in snapshot mode, so it does not persist any change. Where's my mouse? Give a moment to boot up. Oh, wait. What's wrong with this? It didn't show anything? Give a moment for the USB to initialize. There we go. So so the last screen is the Linux VM. So you can use iOS USB. It shows the iOS device is on USB bus. Now we will use iProxy. So this the tool where so this tool will basically forward the traffic from our local port 222. And will forward it to port 44 on the iOS device over USB. So let's do an SSH here. And the password is alpi. Everyone knows that. There we go. We are a root shell inside the iOS VM. I can show it to you using uname. You can see it is running XNU. And the model is currently emulating is the iPhone 12 iPhone 11. You can also run software verse to see the version is currently running. And we can also run other commands to explore the iOS device. Let's start with simple. I will try iOS on the root. You can see there are some files there. You can use htop to list all the process running. So these are real service that runs on real device. So you have running boot, you have install, you have kernel task, you have launchd, basically like an actual device. So in the previous demo, we looked at the restore process of iOS. We even got a bash shell on an installer iOS device, and we also even SSH to the VM using over USB. Next thing, we do have iBoot support. So if you don't know, iBoot is an iPhone bootloader. Is used for recovery or to load the kernel. So why do you want to emulate iBoot? Because iBoot is in the SecureROM chain. So if you can hack iBoot, it will give you a lot of power over the kernel, the software the device is running. So because it is part of the SecureROM chain. And one more reason is that we use iBoot to verify our model, because iBoot tends to use hardware in a really peculiar way, so really weird way. So if you can run iBoot, then we have more chance that our model is emulate the hardware correctly. And our support is pretty experimental, so it's not really ready for production, and it hasn't been published yet. But I will give you a demo right now. So here we go. We start up iBoot. You can see the boot banner on the top left. On the right is the recovery screen that you will generally see. Open up the Linux VM. We can use the iRecovery to query information about the device. And you can also get a shell by using -s. And that's it. Unfortunately, you can also attach a debugger to all these demos. However, for iBoot, we are still pretty new to it, so that's all we got for today. So to recap, iBoot was loaded in the demo, and we use iRecovery in the Linux VM to interact with the recovery mode, which can query some device information and get a recovery shell. However, the recovery shell for release builds tends to be restricted, so there's not much to do with it. Next, we also built TruEMU for rate of fuzzing. So to support rate of fuzzing, we implemented a snapshot feature. So the problem we are trying to solve is that because iOS boot time is not fast enough for fuzzing. So for fuzzing, you want it to run something repeatedly as fast as possible. So we solved that using snapshot. So because snapshot is faster than normal booting, so it reduced the cycle time by 10 times. We also add code coverage support to QEMU because IFL use code coverage for to do its magic. Because we are running TCG, so it's very easy for us to report coverage. So we try to fuzz the USB stack. Here is a simple diagram. So you have AFL running in persistent mode. It will then fork a QEMU process. And the QEMU will start by restoring a snapshot. The snapshot will be at a fuzzable state, so you can start sending commands or inputs to it immediately. Then we have a dummy USB host, which will read inputs from AFL and send it to the iOS VM for processing. So if iOS panic, great, it will be reported to AFL. And if not, no, it will be also reported to AFL for startups. And here's the AFL running USB fuzzing. We also look into Cisco fuzzing. So the diagram is pretty similar. We also have persistent mode AFL. It will fork QEMU, and then QEMU does the snapshot restore. Then inside the iOS VM, we will have a program, the user space program, that receives input from AFL using custom instructions, and will do a Cisco based on the input it gets. If iOS panic, then it will be reported to AFL. Otherwise, it will end the current cycle and do a snapshot restore again. Here's a screenshot of AFL running Cisco fuzzing. We tend to get better speed with Cisco fuzzing compared to USB. However, there's still a lot of challenge for fuzzing. The first is timer interrupts. So these interrupts will interfere with the coverage result, making it pretty random, so it's not consistent at all. Our current solution for that is to mask every interrupt possible. However, without interrupts, our thread is currently the only one running, so iOS will never know if the time slot for this thread has ended or not, so it will never switch to other threads, which reduces our fuzzing hardness. And the second problem is that Apple does not provide sanitizer builds for iOS. So maybe we're thinking about hooking allocator functions, so hooking malloc freeze and try to watch what iOS is doing, but this is still very far from perfect. So let's talk about the future. Well, there are a lot of features we're still implementing, and we want to have it done in the future. We want a proper working frame buffer for the GUI, and also we want the touchscreen to work so you can interact with it like a real device. We also want to emulate SEP because SEP is an essential part to iOS, and as the name suggests, which is Secure Enclave Processor, it contains a lot of security-related functions, so it is an interesting target to emulate. Apparently, we also need to emulate the GPU because the iOS GUI used a lot of GPU, and apparently it refused to work without the GPU implemented. And we also want to improve our fuzzer to get some bugs. So to do that, we need your help. Our code is currently open source at the link on the screen. Or you can add our reverse engineering process to a lot of ways. Or you can either contribute directly to our repo or support the Linux on ARMMAX efforts, because these ARMMAX shares a lot of peripherals with iOS, so it's transferable knowledge. During this, there were a lot of projects that were very helpful to us, especially Asahi Linux team. And also other useful projects are mentioned on the screen. Takeaways. So you can see iOS emulation is totally possible, even though it is not a trivial task. We can also explore a lot about iOS device, iOS hardware, so about hardware through emulation. We also see that how TruEMU enables multiple secret applications such as fuzzing, and we hope that our effort will lower the entry barrier to iOS research. So when more people look at iOS, it will become more secure for all of us. Thank you.